Okay, so we saw the derivative at a point, which was a limit, and finding the slope at a point. Very nice. Let's get out of here. Let's go ahead and find the derivative as a function, because really what we want is a new function. So let's say we have f of x. What we want, so f of x could be anything, it doesn't really matter. What we want is a new function that for right now I'm going to call slope of f of x. This looks weird, but all it's going to be doing is finding the slope of f of x at any x point. So I want a new function where if I know an x value, I can plug it into this slope function and find the slope of f of x. That's what the thing's going to do. Now, that's exactly what a derivative is. And instead of writing slope of f of x, which is kind of cumbersome, we write f prime of x. But that means the slope of f at x. Okay? In physics, maybe you see, like physics, I'm pretty sure, like dots or something over their things, like that. That means the derivative of y, and if you have two dots, that's like the second derivative of y. In calculus, you have f prime, and if you want to do the second derivative, you put another prime. You want a third derivative, you put a triple prime, like that. Okay, but for right now, we're just doing f prime. Okay, so you don't really call it the slope function, but that's exactly what it is. That's just me talking, I guess. Okay, but that's how you should think of the derivative. All it does is find the slope of a function. Now, why that's important? Slope is important for everything, but just as a really quick example, if you know the position graph, we'll call that p of t, position, of anything, anything that's moving, then when you derive it, you find the slope of position, but that's the same thing as the rate of change of position, which is the velocity. Very nice. If you derive velocity, that's the rate of change of velocity, which is acceleration. And that's also the second derivative of position. So if you know the position graph, you can derive it to get the velocity, and if you derive that, you get the acceleration. And you can also go backwards. That's called integration. That's coming up later on in the year. But if you know the acceleration, you can go backwards to get the velocity, and then you can go backwards to get the position. Okay. Anyway, that's not really important right now. It's just that, I mean, that's just one example of why rates of change are good for us to know. So, here's what we're going to start with. I'm going to start with, same as last time, a function, but I'm going to call it x squared, what do you think, minus 7x plus 10, something that factors nice. Okay, and what we want to know is what's the slope, not just at one particular point, because we can always just plug in values super close to each other and find the slope. That's not really calculus, that's just you just doing some, not even algebra, just arithmetic, really, subtracting and dividing. So let's take a look at what this graph looks like. So x squared minus 7x plus 10 is going to factor into x minus 5, x minus 2, which has zeros at 2 and 5. So 1, 2, there's a 0 here. 3, 4, 5, there's a 0 there. And our graph will look, let's do it in, what color do you like? I don't know, purple, blue kind of thing. Okay, this is also going to have a y-intercept of 10, so that's going to be up here somewhere. And you know that by plugging 0 in, you get 10, so it has to go through that. But anyway, so it's got to go through up here because it's got to be symmetric, and let's try this. We'll do this. Oh man, he's getting out of control. Alright, parabola. Wow, there we go. Now imagine this is a nice smooth curve, because it should be. And it goes to this point here. Alright. Now what we want, this is really bad, what we want is the slope of this thing at any point in particular. So like last time we picked an actual point, we picked 1, I think. On this one, I'm going to pick a random point and not even call it a number, I'm going to call it x. So I'm going to pick a point like right here, I'm going to call that x. And the idea is the same. We want to pick another point further down the line, like right here, and find the slope between them. But rather than calling this something new, like y or something, I'm going to call it x plus h. And all that means is it's a little bit bigger than or a little bit bigger than x. H is some small number, so I found a point x, and I found a new point by adding h to x. So 2 points, that's it. And I want to find the slope between them. Well, all that is f of x plus h. That's the y value of this second point. Okay, because you plug in x value and you get the y value, so f of x plus h minus the second y value, which is just the y value at x, which is f of x. All of that over the x value subtracted, so x2 minus x1, so x plus h minus x. And now this is going to find the slope between any 2 points here. Just, I mean, you learned this in Algebra 1, it's just a slope equation. But we don't want any 2 points. We want to bring these points infinitely close together. We want to see what happens as this point here approaches this point here. As they get super close together, what is the slope doing? Because if you just pick 2 points, remember we said that's called a secant line, and that's the average rate of change. We don't want the average rate of change now. We want the slope at 1 point. That's called the instantaneous rate of change, and we'll get into that later. But really, you probably know this already, we want to bring the points super close together, so we let h go to 0. And if h goes to 0, you can see when you plug 0 in for h, you can get f of x minus f of x, which is 0, over x minus x, which is 0. So it's the indeterminate form we've been seeing all year. And all we got to do is a little bit of algebra here and simplify this down. So what we're going to do is I'm going to plug in what f of x plus h is. Well, if f of x is x squared minus 7x plus 10, f of x plus h should be, it's still a limit, f of x plus h, I'm going to draw it here even though this is probably bad, x plus h squared minus 7x plus h, the x's are just becoming x plus h's, plus 10. That's f of x plus h. Now I need to do minus f of x. And you always put this in parentheses because you're subtracting the entire quantity. If you don't put parentheses, you're going to get the wrong answer. And remember, your h's are supposed to cancel out here. And on the bottom will always just be h, because x minus x goes away, just left with h. Okay, now we just need to expand this thing out. So, and these are kind of annoying because, I mean, you got to take up all the space writing this thing out. It's really not too bad because you know everything's going to cancel. It's just a hassle. But you only got to do it for a little bit. No one really does derivatives like this, honestly. It's just you're learning what a derivative is and why it's working. So anyway, I'm just expanding this thing here now. X plus h squared is this business right here. X squared plus 2xh plus h squared. Minus 7x minus 7h distributed plus 10. Now we distribute the negative. Minus x squared plus 7x minus 10. All of that is over h. Now this formula works with any function. Limit h goes to 0 of f of x plus h minus f of x over x plus h minus x. And really these x's aren't even here because they cancel out. So it's really just over h. That is the derivative. This thing right here I'm going to box is called f prime at x. Whereas before we did it, we called it f prime at a, where a was a number. This is called f prime of x. And it is the slope function. It finds the slope of a function. In this case, we're finding the slope of this function, x squared minus 7x plus 10. But if you plug a different function into there, you're going to simplify it differently, get a different answer, and that will be the slope function. So anyway, you can see what's going to happen here. Let's go to a cancel color. What's a good cancel color? It doesn't matter. Gray. All right, gray might be best, but we'll do it. X squared minus x squared. Goodbye, x squareds. They're gone. Minus 7x plus 7x is going to go away. Plus 10 minus 10. And that will always happen. As long as you do everything correctly, that's going to happen. And what we're going to get now is, we'll stick with gray. The limit, h goes to 0. So again, I'm still writing the limit up front because I haven't plugged in 0. Okay? But I also haven't really changed this thing at all. I've just simplified it down. So it's still the same exact thing. It's like $1.04, which is an example I always use in class. They're the same thing, they just look different. That's exactly what we're doing here. Same exact thing, just looks different. So 2xh plus h squared minus 7h, that's a 2 here, I promise. And that's all that's left, over h. And now we can split up this division. Remember, multiplication distributes through pluses and minuses, so does division. So dividing by this h, you have to divide every single one of these terms up here by h. So now we need a new cancellation color. We'll pick this guy. So this h is going to cancel with this h. It's going to cancel this square to make it h to the first power, and it's going to cancel with this h. And now h is still going to 0. Let's go to the next page here. So we're going to have limit h goes to 0. Oh, come on now. The limit as h goes to 0 of 2x, because the h is canceled. I forgot what it was already. Plus h minus 7. There we go. Plus h. Oh, plus h minus 7. And now what we've done here, when we canceled out that bottom, when those h's canceled, remember back to limits here, when you cancel out that bottom, what you're really doing, since it cancels on top and bottom, you're canceling out a whole. Okay? So even though, now you can think of this whole big nastiness here, and this whole, what it simplifies down to, as a big graph if you want. Not this graph, it would be the graph of the slope, as the points move close together. Really not that important, but essentially when the things cancel out, when h cancels out like that, that means there was a hole there, which means the limit's going to exist. And now we can plug in, because this thing is equal to that big fraction we just saw, except for at the point where h is 0. And we don't care what happens at h equals 0. We care what happens as it approaches 0. And I'm going to throw all my reasons here. This thing is continuous. 2x plus h plus 7 is continuous. Even though there's two variables there, it's a continuous thing. And as h goes to 0, it approaches 2x plus 7. And that is what we call f prime of x. So you might see the question, find the slope. Or you might see, instead of slope, the instantaneous rate of change. That's a rate of change. Okay, rate of change. Okay, slope, instantaneous rate of change, same exact thing. Or you might see f prime of x. Every single one of these, 1, 2, 3. They mean the same thing. Find the slope, find the instantaneous rate of change, find f prime of x, whatever. And it would say at, and it'll give you a point. X equals like 3. Okay, so find f prime of x at x equals 3. Well, we just found f prime of x for all x right here. So really they're asking for f prime of 3, regardless of how they say it. We want f prime of 3. When you plug in 3, you get 6 plus 7. That's 13. Awesome. One great thing about this is, let's go back to what our graph looks like. The slope of this thing should be 0, where the minimum is, at the vertex. And you can see that right here. Okay? For an instant, the slope on this side is negative because the function is decreasing. The slope on this side is positive because it's increasing. But when it goes from negative to positive, since it's a smooth curve, the slope must go through 0. So somewhere the slope has to be 0 in there. And that, hopefully you know this, is the vertex. It's just the very minimum of this parabola. Now, what the derivative does, now let's say we didn't know where the vertex was. What the derivative allows us to do is, we can take the derivative and we can say, I want to find the vertex of my function. Well, I know the vertex has to happen when the slope is 0. Well, I'm looking for an x value, and I know that I want the x value to give me a slope of 0, so all we're going to do is say f prime of x, which is 2x plus 7, I want f prime of x to be 0. I want the slope to be 0, because that's what I'm looking for, that's what the vertex is going to be. And now I solve this. And this is just a simple equation, minus 7 divided by 2. Negative 7 halves is x. Oh, it's a minus 7. This makes way more sense with the minus 7 in there. That's not right. Man, oh man. I made a terrible mistake. I apologize. I think I got an eraser in here somewhere. Here we go. This is minus. Man. So this is minus. I'm sorry. I'm not doing this again though. So this means this changes too. Let's get this out of here. Okay, and that means this is wrong. It's going to be positive 7 halves. Same thing. I just wasn't paying attention here. Just like a teacher. Alright, so this was minus here. 2x minus 7 is the derivative. This is still a plus. This was a minus. So now when you plug in 3, I'm sorry, that's over here. Plug in 3, you get 6 minus 7, that's negative 1. There we go. When you solve this for 0, this is a minus here. So you add 7, divide by 2, you get positive 7 halves. So that's where the vertex is, x equals 7 halves, which is 3.5. Well, let's go back to our graph, and you can see that at 1, 2, 3.5, whoa, this thing has the vertex right there. We also saw at negative 1, we found the slope at negative 1. That was right here. F prime of 3 is negative 1. You can look at your graph. F prime of 0, or 0, 1, 2, 3, it's right here, has a slope of, what's going on here? Negative 1. Let's change colors. So right here, there's a slope of negative 1. And then here, there's a slope of 0. What's up, Sabrina? Just rambling to myself. Yeah. Okay. We're all done here.